Good morning, good afternoon, people of Earth, and welcome to our Facebook Live here at the SETI Institute. My name is Franck Marchis. I'm a researcher at the SETI Institute, and today we're going to have a special Facebook Live with John Jenkins. Hi, John.
Hi.
So John is an astronomer at NASA and also the lead of the Science Operations Centers over there. John is involved in the TESS mission, and today we're going to talk about TESS.
All right.
Right? So let's start first. Tell us a bit about what is TESS, just a summary. I know most of our people here, they know what TESS is about.
Okay.
But give us a brief overview of the mission.
Right, so TESS is an Explorer mission that was launched in April of 2018, just a little over a year ago. Its job is to perform an all-sky survey for transiting planets around nearby stars so that we can follow up and characterize the planets that we find throughout the mission. And it does this by basically having 4 telescopes, each of which has a field of view that's 24 degrees by 24 degrees. So it reaches up 96 degrees. So we're observing roughly 1/26 of the sky at any given time. Mm-hmm. And every month we change the field of view to look at another slice of the sky. And after 1 year, we've completed 13 fields of view and have covered 1 hemisphere. In fact, that's what we just did. We just completed our survey of the southern hemisphere. And just about a month ago, a little less than a month ago, we flipped the spacecraft upside down, and we're actually observing the northern hemisphere now. And we're actually observing a very special field at the moment, and that is the Kepler field of view that was observed for 4 years during the primary Kepler mission.
So you're observing the same area of the sky that Kepler have been observing for 4 years, basically.
That's right. That field of view is encapsulated by our much larger field of view that TESS has. The field of view for Kepler was about the size of the palm of your hand held at arm's length, and that allowed us to observe over 100 square degrees. But in fact, the field of view for TESS is about 2,300 square degrees, so it's more than 10 times larger. It's a huge fraction of the sky.
So it's a huge fraction of the sky that you look for 27 days.
Right.
And you measure the photometry of stars, all of them, or what type of stars typically you focus on?
Right. So we have a target list of 20,000 stars that are sprinkled over the 4 cameras, and we observe those stars at 2-minute cadence. So we store the images or postage stamps containing these stars every 2 minutes, and every 2 weeks we download that data to the ground. We do that twice, and then that's 1 field of view that we cover. We also, above and beyond the 2-minute postage stamps, also collect the full frame images every half hour. So Kepler, as you might recall, targeted 165,000 stars at a given time at the maximum, and it sampled those every half hour. But it only sent down the postage stamps for those 165,000 stars. So it was roughly 5 or 6% of the total image was brought down to the ground, and we threw away all the other pixels. TESS has more than 10 times the storage capacity that Kepler did. It's about 10 times newer technology that we were able to fly.
SD cards are significantly better now.
Yes, we're also in a high Earth orbit, which means that it's an orbit that's highly elliptical. It's in resonance with the moon. It's exactly 1/2 the orbital period of the moon. So when we're up at our furthest distance from the Earth, and the moon is either 90 degrees this way or 90 degrees that way, and then we come in to as close as 17 Earth radii from the Earth, and the maximum is about 59 Earth radii, so it tells you how eccentric the orbit is. Mm-hmm. And because we're so close to the Earth, we can download a lot more data much more quickly than we could with Kepler itself, although we're using the same radio frequency to communicate. It's just we're so much closer than we were with Kepler. We can store a lot more data, we can download a lot more data.
Okay, so the spacecraft has been launched in April. It started scientific operation in July last year.
That's right.
Right? So it's been a year now, roughly.
That's right.
And a few weeks ago, you were at this TESS conference. That was basically a conference where people from everywhere in the world, which has been using TESS data to do some science, has presenting their work.
That's correct.
Yeah.
Absolutely.
So give us kind of the highlight. I heard of 20-ish planets has been seen with TESS, but you have also what we call candidates.
Right. So every month we actually take the data down from the spacecraft, and the data get piped to Ames Research Center from MIT, which is leading the mission, and there's where they have the Payload Operations Center that manages the instrument. We take the data and we run it through our pipeline, and we use the NAS Pleiades supercomputer to be able to do all the number crunching and keep up with the data. In fact, it takes us about 5 to 6 days or so, 5 to 7 days to process 1 month of data once we get both orbits down. And part of that is to extract the brightnesses of the stars, as you said before, to look for instances where a planet crosses the face of its star, blocking a small fraction of the light over a period of typically an hour to several hours to half a day for very long orbits. And we also run a search algorithm that identifies transit-like features or dips in the light curves that might be planets. We take those transit-like features, we fit a limb-darkened transit model, so we bring physics into the equation, so to speak. We also perform a suite of diagnostic tests that allow us to separate true planets from those cases where we're likely being spoofed by either a background eclipsing binary or by scattered light features or other instrumental systematics. So those lists typically around 1,200 transit-like features, along with all the light curve and the calibrated pixel data products, go back to MIT. And there's a vetting team at MIT, but also they have helpers from around the world, so to speak, to review the diagnostics coming out of the pipeline and then to determine which objects should be promoted to TESS objects of interest. So that's the next step in the discovery process. So those objects of interest then are ones that we feel are likely to be planets. Not all of them are planets. Indeed, some of them are false positives. But they're good test cases and can be followed up from the ground. We have a very active follow-up program where we have several teams devoted to several different kinds of follow-up. For example, we have a team that actually does photometry from the ground on objects that are bright enough and have deep enough transits that you can actually directly confirm the presence of the planetary transits.
So they use ground-based telescope to confirm basically the existence of this transit.
Right. In some cases that works that way. Yeah. And the advantage that you have on the ground is that you have much higher spatial resolution on the sky typically. TESS is observing such a big part of the sky that the pixels are 21 arc seconds across, which is actually
the size half the size of Jupiter in angular size.
Right. So there's a lot that can be hiding underneath the pixels that are the image of a star, and so the ground-based follow-up programs look at resolving which object, which star is likely the source of the transit like features, and in some cases we can actually directly measure the transits. In other cases we're simply using high-resolution imaging in order to identify whether there are other stars nearby that could be the source of the transit-like feature, and thereby requires more scrutiny and contemplation before we actually confirm it as a planet. We also do radial velocity observations that allow us to measure the masses of many of these planets and also look for unseen companions that are not transiting but give a radial velocity signature because of their mass dragging the barycenter of the system and the star around the barycenter of the planetary system.
So I have a question, but before this I want just to mention to our viewers that whoever they are and where they are watching us, that they can ask questions on our Facebook Live as well. I will take a few questions in a few minutes. So something very interesting you mentioned is that TESS is observing very close stars, like typically 150 or 200 light years.
Right, especially for the small cool red dwarfs. We're especially targeting M stars within 200 light years. So if we compare that to Kepler, Kepler was looking at a field of view that was essentially a light cone, and the stars were typically between 1,000 and 3,000 light years away.
So they were faint for most of them?
They were faint, relatively speaking, compared to the kinds of stars that are bright enough that you can actually do a lot of radial velocity follow-up to measure the masses. In fact, that's what motivated TESS, was that Kepler was highly successful. It taught us that on average every star that you look up in the night sky has at least one planet. And so now that we know that planets are plentiful and just about everywhere you look, then we can afford to fly a mission with less spatial resolution, but that is capable of capturing the light from many more stars that are much closer. And so the stars are typically 10 times closer and 100 times brighter. So you have 100 times as many photons. That means you can run that light through a prism, spread it out, and do spectroscopy. That allows you to do radial velocity. And later on, we hope that many of these small, potentially rocky planets can be followed up with other assets like James Webb Space Telescope, the 30-meter telescope, Gemini, and other assets, other assets to actually follow up and characterize the atmospheres of these planets. And eventually, we hope that they will serve as great targets for LUVOIR, HabEx, or other missions capable of actually looking for biosignatures in the atmospheres of these planets to detect life.
So yeah, in short, when you look at the sky, you don't see stars, you see planetary systems. And what TESS is doing is to basically give us a map of the most interesting planets nearby us. And using this map, we'll be able to use facilities from the ground and the future space mission to characterize those planets and to sniff the atmosphere and maybe find life on those exoplanets. That's why we work at the SETI Institute, right?
Right.
So there is a few interesting systems that has been announced recently. One of them, I have I can show a few pictures here. One of them, we can start with this one. This is beautiful name, L9859. So I'm pretty sure you know this by heart. So, L9859b is an interesting one because that's basically a very small terrestrial exoplanet. It's there is on this picture here. You can see the relative size of this exoplanet compared to Earth. So those are artistic pictures, right?
Right, that's correct. So we don't know what these planets really look like.
What we see is the shadow of the planet.
That's right. We see the shadow. We can inform our imagination, so to speak, to enable artists to render a planet based on its proximity to its star. So we do know a lot about the stars. We know their effective temperature. So we know how intrinsically bright they are. We know the distance of the planet from the star from Kepler's law. So we measure the interval between transits, and one interval is one orbital period. But if we know the mass of the star, which we can get quite readily for these bright stars, then we know the distance from the star that the planet is situated. That tells us what the insolation or how much radiation the planet is receiving from its star, and then we can make guesses as to what the conditions are like on the planet to inform the colors that are chosen for the rendering and the composition of the planet itself based on that.
This system has 3 planets. The central star is what we call an M-type star. So it's one of the most numerous planets stars in our galaxy. I think 75% of the stars in our galaxy are M-type stars, so they're very common. And those planets orbit very close to their stars. Like typically in this case, is 2 to 7 days.
Right.
So that's a typical system we have seen with Kepler and with ground-based mission, and now we can see as well with TESS. Another system, I think, let's talk about TOI 270. So TOI 270 is this. It's once again a multiple planetary system. 3 planets been detected around this one. What we have in this case, I'll let you talk about this if you want to prefer. But what's the main difference between this one and L98-59? What's the main characteristic of this system?
Well, in this case, we have 3 planets, but 2 of them are mini Neptunes or super Earths, and they're not all terrestrial. They're not all about the same size as Earth.
Can you explain to us what is a mini Neptune? Because I've never heard about this.
Yes, so most people don't know about super Earths or mini Neptunes because we have none of these objects in our own solar system. So we go from the terrestrial planets, of which Earth is the largest terrestrial planet in our system, or the largest rocky planet at 1 Earth radius by definition, and all the way to the next largest planet is Neptune, which is 4 Earth radii about. And so there's this gulf, this void between 1 Earth radius and 4 Earth radii. And it turns out that nature loves to fill this void because, as Kepler has shown us, most of the planets we discovered with Kepler were between 1 and 4 Earth radii. In fact, most of them were below about 2 Earth radii. And so we don't have any of these creatures in our menagerie here in our own solar system. So they're they're very curious objects that we want to learn about because it seems that most of the planets we find fall into this category. And the biggest question is whether a planet between 1 and 2 Earth radii can be rocky. And so Kepler has actually given us very strong clues, especially in the light of the Gaia observations, which revolutionized our understanding of the stellar properties so we could better understand the planetary properties. But it seems if you look at a histogram of the distribution of the number of planets per star as a function of size, that there's not one hump between 2 and 1 Earth radii, but rather there are 2 humps. And below about 1.8, 1.7 Earth radii, there's a population of planets that go down to 1 Earth radius and below. And we believe that those are most likely to be rocky planets. And then there's another hump that carries you up to 2 Earth radii and then beyond that are most likely to have considerable gaseous envelopes and be more like mini Neptunes than super Earths in the sense of being super rocky planets.
And in this case, because this star is nearby and quite bright, it will be possible using JWST or any 8-10 meter class telescope to maybe characterize the atmosphere of those planets and finally find out the composition of those planets, maybe understand the physics behind the
That's
formation.
right. And especially around these M stars that are relatively close and also relatively bright. Some of these small rocky planets, almost certainly rocky planets, are some of the best cases for follow-up to actually determine and characterize their atmospheres if they have any. They are very close to their star, and so there is an open question as to whether they retain their atmospheres. In fact, the sorting of the planets into the rocky Earth-sized planets or near Earth-sized planets and the mini Neptunes, we believe that many of the planets in this category are very close to their star, and that many of them likely started out as Neptunes or giants. They evolved inwards, migrated inwards, and have lost most of their atmosphere through photoevaporation. And so the story is not
so that's
simple.
an evolution of the planet. Maybe they are in fact similar planets, but one has lost its atmosphere by getting closer to its stars, and the atmosphere get evaporated, and then we have just the central core.
That's right. We may be looking at stripped cores in some of these cases. And so there's likely a big difference between a truly Earth-like planet in the sense of it forming at a distance where you can have liquid water pooling on the surface, which we're all very interested in. It may be that as we move out in terms of the orbital distances, that the sorting of the planets by planet size is somewhat different. It's just the case that the planets that are closest to their stars are the easiest for us to find, whether it be by the radial velocity method or by the transit method. So there's an observational bias towards finding these systems. On the other hand, these are the systems that are most easy for us to follow up and characterize. So these are the ones within reach in the next 10 to 20 years to actually characterize and follow up in great detail.
Yeah. So let's finish with this one. Another beautiful name, JG357.
Right.
So that's another M-type star, a dwarf star once again, like all of the other one. And this system has a very interesting planet, which is called JG357d, because it's B or D? I always forget. It's D, yes, D. Because D orbit in the outer part of what we call the habitable zone of the star.
Right.
So what does that mean? What is the habitable zone? Probably people know, but let's remind us.
Right. So the habitable zone is very difficult to define. We have some working ideas as to what might be represented by the habitable zone. There are some heuristic borders or end cases. So we know that it's likely there was liquid water on early Mars from alluvial features that we see in other evidence on Mars. And so that represents, in some sense, the outer limit or the outer boundary of the optimistic habitable zone. We also believe that early Venus also had a liquid ocean. And so Venus's orbital distance of 0.7 astronomical units presents the inner radius of the optimistic habitable zone. But there are evolutionary models for planetary atmospheres that give us less optimistic boundaries, but they're in some sense not fully informed because we don't know everything we need to know to fully specify what makes the habitable zone. But those models give us ideas as to what the inner radius is at which you can still retain enough liquid water to be habitable, and the outer radius beyond which you would get too cold and freeze it out. In this case, planet D, 357D, was not discovered by TESS, but rather by the follow-up observations. There had been many observations, radio velocity observations of the star over time, and so when we found the innermost planet through TESS by transit photometry, then the astronomers and scientists went back in the historical record to look at the existing radio velocity measurements and made further radio velocity measurements to better characterize the system, but discovered 2 additional planets, neither of which transits in the TESS data that we've collected to date.
So we have the mass of this one, D,
that's
and
right.
the mass of C, and we have the size of B.
We have the size of B, and we have an upper mass limit on B. We don't know what the sizes are of C and D, but our best guess is for D is that it would be about 1.75 Earth radii. So that sort of puts it at the boundary between being a mini Neptune and being a rocky super Earth. But I'd be more willing to bet on it being a mini Neptune given its size.
So we're really like right now discovering those new worlds and characterizing them. You say we discovered 20-ish planets officially with TESS?
We've confirmed and published on the order of about 24 planets to date, and there are, of course, other teams outside of the TESS science team which are following up and confirming some of these planets as well, including citizen science projects like Planet Hunters.
Yeah. So because there is a lot of work to do to basically detect those transits. You mentioned there is probably an algorithm looking at that, because you don't look at the data by eyes. You don't personally every night look at the light curve of thousands of stars, right?
No.
You don't do that. You have something else to do.
That's fun for a little while.
Yeah. So citizen science, apparently people can help you, right?
That's right.
Recently, they announced the discovery of a Kepler planet in the K2 survey with citizen science by looking at transit. So people can contribute, do the same with TESS on the same
Absolutely,
place?
absolutely. There's a Planet Hunters project now for TESS. In fact, they've published at least one paper on a planet that is currently right now officially the longest period planet to date discovered in the TESS data.
We're talking about 100 days here, or because everything was like 5, 10, 50 days for this one.
I think it's in the 70s.
Okay.
It's just under 80 days, like 79 days or something. And so, in fact, because we do our multi-sector search only every so often, so we did it after 2 sectors, after 3 sectors, after 6 sectors, after 9 sectors, and then we waited to collect the remaining sectors of the southern hemisphere, and we just ran our sector 1 through 13 search.
Okay.
And so we're about to get those results back to the science office for vetting. And so we expect to find longer period planets because we have a year's worth of data to search through. But because most of the time we're just searching through a single month of data, then we require at least 2 transits for our algorithm to say, hey, there might be something here. But Planet Hunters allows people to view individual sector light curves and to identify, click on features which they believe are consistent with being transits. And for a really deep single transit, we wouldn't find it because we're not looking for deep single transits, but they can note it and then bring it to the attention of the astronomers associated with Planet Hunters, who can then do follow-up and confirmation. And so they can beat us out before we actually get to our multi-sector search. Or in some cases, we only observe that star for just that one 27-day period. We're not going to observe it again until the extended mission at some point in time, but it's a very convincing single transit.
So you just need to have an internet connection,
That's
and
right.
a computer, and then you can be a planet hunter, basically, and contribute to this research.
Absolutely. And one of the fascinating things about TESS is that we are observing stars that are relatively close and relatively bright. So it's very possible, in fact, a lot of amateur astronomers are following up and observing the systems that we're discovering simply because we have so many photons for them to get into their telescopes, so they can actually participate and follow up and actually generate additional information especially in those cases where we only observe for 1 month. The larger planets with the deeper transits can be followed up from the ground by amateurs who can then refine our knowledge of the orbital period of these planets in time for us to take advantage of James Webb Space Telescope. Because if you only observe for a month, then by the time James Webb flies, your uncertainty about when the transits are going to occur may be on the order of days, in which case it's going to be very hard to schedule that very unique and very expensive asset to say, I don't know where it is, I want you to observe for 2 days for this 1 hour feature.
So amateur astronomers who have a telescope can basically contribute as well by observing the stargate again and detecting another transit, refining the orbit of the planet.
Yes, absolutely.
And then in the future, when JWST or any other space mission will be available, you'll be able to precisely time when this transit will occur. So it will basically save a lot of JWST telescope time.
That's right.
An hour of JWST will cost probably more than $150,000. So
Right.
we are saving a lot of money thanks to amateur astronomers' contribution in this case.
That's possible. That's a very exciting aspect of this mission, is that amateur astronomers can directly increase the value and the science output of this mission and of future missions like James Webb, because it's a very valuable asset with a limited time horizon for us to be able to use it, because of the cryogen on board will only last for, I think, 6 years is the lifetime. Is that
That's
right?
6 years the lifetime of TESS at the moment?
Of James
Of
Webb.
James,
I believe so. So it's an invaluable contribution that amateurs can make to the future science.
Yes, so there is a group at JPL who's basically organizing this amateur astronomer follow-up, the exoplanet transit survey.
Okay.
And Unistellar, the telescope we are building, and for citizen science here at the SETI Institute, the SETI Institute, is basically capable of also detecting transiting exoplanets. So
that's
we will also
wonderful.
contribute.
I mean, Frank, I was a child when I only dreamed of being able to know whether there were planets around other stars, and I think it's just wonderful that amateurs can look up into the night sky with their own equipment and see evidence of transiting planets. And
I do remember in the 90s when people were trying desperately to find those transiting exoplanets with those large surveys, and they could not detect anything because of instrumentation problem. And now, amateur astronomers can do it in their garden. It's unbelievable.
It is unbelievable. It's the march of technology, both in terms of the detectors. So with the mid-90s, the backside illuminated CCDs became commercially available and nearly doubled the sensitivity of these light gathering devices, light counting devices. And then computational assets. Computers have gotten so much faster and so much more capable, and so it's not a problem for amateurs to collect the volume of data they need to collect as they observe to help confirm and follow up these discoveries.
So I have another question. So TESS was launched to find exoplanets, right? But what interests us at the SETI Institute is, of course, to see and find an exoplanet like Earth, a cousin of Earth, something which orbits around a G-type star at 1 AU or in the habitable zone.
Right.
Is this going to happen? Is TESS?
TESS is not designed to find an Earth analog. We may get lucky with our, as we go through the extended mission, we'll be continuing to observe the same sky that we've observed before. In fact, we're going to continue in the extended mission, which we just got approved for, to observe the northern hemisphere for a while after. So we'll repeat some of the observations, and especially for the stars that are in the continuous viewing zone. So we have one camera, it's called the pole camera, and we typically just rotate around that camera. Now, with the northern hemisphere, the Earth and Moon are getting in the way, so we've actually shifted it up so that it's not the top camera, but the second camera that is performing that function for a few months before the Earth and Moon get out of the way and we can go back to our normal observation strategy. But that means that we'll have potentially, through the extended mission, several years of observations on these stars, and so we'll be able to look for periods and longer period orbits around the stars. So we may indeed find some habitable zone planets around G stars, but in fact, that's not the principal goal of TESS. TESS is designed to find at least 50 small planets less than the size of Neptune who we can measure their masses. And then those would be around the bright stars, relatively speaking, that would be the best targets of opportunity for follow-up and characterization with James Webb. And in fact, James Webb is not, nor WFIRST are going to be able to characterize the atmosphere of a true Earth analog. That's going to come later. So the job of TESS is to find a catalog of planets that we can follow up in the near term, the next 20, 30, 40 years. And then we'll have to think of other ways to find habitable zone Earth analogs beyond what Kepler has done for us already.
All right. Well, that's a very nice way to finalize this SETI talk. Thank you very much, John.
Well, thank you, Franck.
We are going to see each other in a year to talk about the new TESS exoplanets, probably, right?
Okay.
You are welcome to
That's
talk,
right.
to come here back.
And we'll be able to talk all about the extended mission, which is going to feature some important changes in the data collection.
All right. Thank you very much to our viewers, wherever you are on this planet. Thank you for following us. Don't forget to join our Facebook page if you want to see and watch the next Facebook Live. Write your comments, like us, post about us, share our post, and once again, thank you for your interest in planetary science, and thanks again, John, for joining us.
Well, thank you, Franck. I'm very pleased to have been here.
Bye-bye.